Every atom in your body was forged inside the nuclear furnace of a dying star, yet the very existence of those atoms defies everything our everyday experience tells us about reality. Right now, as you listen to this, electrons in your brain are tunneling through energy barriers that classical physics says should be impossible to cross, while the space around you ripples with gravitational waves from cosmic collisions that happened billions of years ago. This is not science fiction. This is the extraordinary universe we actually inhabit, where the smallest particles exist in multiple places simultaneously, where massive objects warp the very fabric of space and time, and where stars die in explosions so violent they outshine entire galaxies. Tonight, we are going to explore the deepest mysteries of existence itself, from the quantum realm where reality becomes probability, to the cosmic dance of space-time, to the spectacular deaths that seed the universe with the elements of life. Welcome to Calm Scientist, where we explore the wonders of our universe in the perfect atmosphere for bedtime learning. I'm your guide through tonight's journey into the fundamental nature of reality. Fair warning, this might be too fascinating for sleep, but that is a risk we are willing to take together. If you find yourself genuinely enjoying this exploration of cosmic mysteries, I would be grateful if you could like this video and subscribe to join our community of curious minds. I would love to hear from you in the comments. Tell me where you are listening from, what time it is there, and the weirdest dream you have ever had. There is something magical about knowing we are all scattered across the globe, united by curiosity about the same magnificent universe. Tonight we will journey through quantum mechanics, the nature of space-time, stellar evolution, and the violent deaths that create the very elements we are made of. Let us begin our journey by exploring the most counterintuitive realm in all of science, where particles can be in multiple places at once, and reality itself seems to depend on whether anyone is watching. Picture yourself standing at the edge of a vast ocean on a moonlit night. The waves roll endlessly towards shore, their peaks and valleys catching fragments of silver light. Each wave seems to blend seamlessly into the next, creating patterns that dance across the water's surface. Now imagine that same ocean, but frozen in time, each droplet suspended in perfect stillness, each molecule distinct and separate. This is the paradox that lies at the heart of our physical world, a mystery that took humanity centuries to even begin to understand. We live in a universe governed by quantum mechanics, though most of us never realize it. Every atom in your body, every photon that brings light to your eyes, every electron that powers the device you might be using right now, all of these exist in a realm where the familiar rules of everyday experience simply don't apply. This is not a distant theoretical concern. This is the foundation of reality itself. The journey into quantum understanding begins with a simple question that plagued scientists for generations. What is light? Is it made of particles, tiny bullets of energy that zip through space in straight lines? Or is it a wave, an undulation in some invisible medium that fills the cosmos? For 3 centuries, brilliant minds wrestled with this question, never imagining that the answer would revolutionize our entire conception of existence. In the early 1600s, a brilliant mind named Isaac Newton proposed something that seemed perfectly logical. Light, he suggested, must be made of tiny particles, little packets of something that travelled in straight lines and bounced off surfaces just like miniature billiard balls. This made sense to people. After all, light creates sharp shadows, and shadows seem to suggest that light travels in straight lines, blocked by obstacles in its path. When you hold your hand up to block the sun, you create a distinct shadow with crisp edges. Waves, Newton reasoned, would bend around obstacles and create fuzzy, indistinct boundaries. Newton's corpuscular theory of light dominated scientific thinking for over a century. It explained reflection beautifully. When light bounces off a mirror, it behaves exactly like a ball bouncing off a wall, with the angle of incidence equaling the angle of reflection. It explained why light travels in straight lines through space, creating the geometric patterns of shadows we observe every day. It even explained refraction, the bending of light as it passes from one material to another, by suggesting that light particles speed up or slow down depending on the medium they encounter. But even as Newton was developing his particle theory of light, a Dutch physicist named Christiaan Huygens was reaching a very different conclusion. Huygens observed the way light bends around corners, the way it creates interference patterns when it passes through small openings. To him, these behaviours suggested that light was not made of particles at all, but was instead a wave, rippling through some invisible medium that filled all of space. Huygens developed a comprehensive wave theory of light that could explain phenomena Newton's particles could not. When waves meet, they interfere with each other. If two wave peaks meet, they add together to create a larger peak. If a peak meets a trough, they cancel each other out. This interference could explain the complex patterns of light and shadow that appeared when light passed through multiple openings or around obstacles. For nearly 2 centuries, these two ideas battled for supremacy. The wave theory gained ground when scientists began to observe phenomena that particles simply could not explain. In 1794, Augustin Jean Fresnel demonstrated that light could indeed bend around obstacles, creating patterns of bright and dark bands that were exactly what wave theory predicted. The nail in the coffin of pure particle theory seemed to come with Thomas Young's famous double-slit experiment in 1801. Young's experiment was elegantly simple yet profoundly revealing. He took a beam of light and directed it toward a barrier with 2 narrow slits cut side by side. Beyond this barrier, he placed a screen to catch whatever light made it through. If light were made of particles, you would expect to see 2 bright bands on the screen, one behind each slit, with the light particles piled up after passing through. But that's not what Young observed. Instead, the screen showed a pattern of alternating bright and dark bands, exactly what you would expect if light were a wave interfering with itself. The light passing through one slit was interfering with the light passing through the other slit, creating a pattern of reinforcement and cancellation. When the waves from both slits arrived at the screen in phase, they created bright bands. When they arrived out of phase, they cancelled each other out, creating dark bands. Think about that for a moment. The very nature of light seemed to be resolved. Light was clearly a wave phenomenon. But the universe had a surprise waiting, one that would shatter this comfortable certainty and launch physics into an entirely new realm. In 1905, Albert Einstein examined a puzzling phenomenon called the photoelectric effect. When light shines on certain metals, it knocks electrons loose from their atoms. The strange thing was that the energy of these ejected electrons didn't depend on how bright the light was, but rather on the colour of the light. Dim blue light could knock electrons free, while bright red light could not. This made no sense if light were purely a wave. According to wave theory, brighter light should carry more energy and therefore should be able to knock electrons free with greater force. The colour of the light should be irrelevant, only the intensity should matter. But the experiments showed exactly the opposite. It was as if each individual interaction between light and an electron involved a specific amount of energy that depended only on the light's frequency, not its amplitude. Einstein proposed something radical that harked back to Newton's original particle idea but with a quantum twist. What if light came in discrete packets of energy, little bundles he called photons? The energy of each photon would be proportional to the light's frequency, following the relationship that Max Planck had discovered a few years earlier while studying blackbody radiation. This would explain why blue light, with its higher frequency, could liberate electrons that red light could not touch regardless of intensity. Each blue photon carried enough energy to knock an electron free, while red photons individually did not. This photon concept explained the photoelectric effect perfectly, but it created a new puzzle. How could light be both a wave, as Young's double-slit experiment clearly demonstrated, and a particle, as the photoelectric effect seemed to require? The answer, it turned out, was that light is neither a classical wave nor a classical particle, but something entirely new that exhibits properties of both, depending on how you observe it. Suddenly, both Newton and Huygens were right, and both were wrong. Light exhibited both wave and particle properties, depending on the experimental setup. When you looked for wave behaviour, you found waves. When you looked for particle behaviour, you found particles. But you could never observe both aspects simultaneously. This complementarity, as Niels Bohr would later call it, became one of the foundational principles of quantum mechanics. But this was just the beginning of the mystery. If light, which everyone had assumed was purely wave-like based on interference and diffraction experiments, could also behave like particles, then perhaps the reverse was also true. Perhaps matter, which everyone knew was made of particles, could also behave like waves. In 1923, a young French physicist named Louis de Broglie made an extraordinary leap of imagination. If If Einstein's photons could have both energy and momentum despite being waves, then perhaps material particles could also have wave-like properties. De Broglie proposed that every piece of matter in the universe, from the smallest electron to the largest star, had an associated wavelength inversely proportional to its momentum. This was not merely theoretical speculation. The wavelength de Broglie calculated for electrons was small, but potentially observable under the right conditions. If electrons truly had wave properties, they should create interference and diffraction patterns just like light waves do. The challenge was designing an experiment delicate enough to detect these effects. In 1927, Clinton Davison and Lester Germer, working at Bell Laboratories, fired a beam of electrons at a nickel crystal and observed the telltale signs of wave interference. The electrons scattered from the crystal in patterns that could only be explained if they were behaving as waves with exactly the wavelength de Broglie had predicted. Simultaneously, George Paget Thomson in England demonstrated electron diffraction using thin metal foils, providing independent confirmation of matter waves. The implications were staggering. If electrons could behave like waves, then the very atoms that make up everything around us were operating according to principles that defied common sense. An electron orbiting an atomic nucleus wasn't like a tiny planet following a predictable path around its sun. Instead, it existed as a probability cloud, a ghostly wave of potential that could only be pinned down to specific locations when someone bothered to look. This brings us to one of the most profound insights in all of science. When we say an electron behaves like a wave, we don't mean it's moving up and down like a wave on water or oscillating back and forth like a vibrating string. We mean that its very existence, its probability of being found at any particular location, is spread out in space according to mathematical relationships that govern waves. The electron doesn't have a definite position until the moment we measure it. Before that measurement, it exists in what physicists call a superposition, a state where all possible locations exist simultaneously. Imagine trying to photograph a hummingbird in flight, but instead of capturing a single clear image, your camera somehow records every possible position the bird might occupy at that instant, all superimposed on a single frame. That's closer to how quantum particles exist before measurement, though the analogy barely captures the strangeness of the actual phenomenon. The quantum world isn't just fuzzy or uncertain, it's fundamentally probabilistic in ways that have no analogue in everyday experience. The mathematics that describes this behavior, developed primarily by Erwin Schrödinger, treats particles as wave functions, mathematical objects that encode the probability of finding the particle at any given location when a measurement is made. These wave functions evolve in time according to Schrödinger's equation, spreading and interfering and diffracting just like classical waves. But unlike classical waves, which represent actual physical disturbances in some medium, quantum wave functions represent pure information, the ghostly realm of possibilities that exists before the concrete world of measurement outcomes. Werner Heisenberg, working in the same era as de Broglie and Schrödinger, discovered something even more unsettling about the quantum world. It wasn't simply that quantum particles were hard to pin down because of experimental limitations or technological constraints. Rather, they were fundamentally impossible to pin down completely due to the very structure of quantum reality itself. His uncertainty principle, formulated in 1927, states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments, or a consequence of clumsy experimental technique. This is a fundamental property of reality itself, built into the very fabric of space, time, and matter. The mathematical expression of the uncertainty principle is deceptively simple. The product of the uncertainties in position and momentum must always be greater than or equal to Planck's constant divided by 4 pi. Planck's constant is an incredibly small number, about 6.6 times 10 to the minus 34 joule seconds, which is why quantum effects are negligible at the scales of everyday experience. But for particles like electrons, this fundamental limit becomes the dominant factor in determining their behavior. Think of it like this. If you want to find out exactly where something is, you need to interact with it somehow, perhaps by bouncing a photon off it and detecting where the photon goes. but the very act of bouncing a photon off a particle transfers momentum to that particle, changing its velocity in an unpredictable way. The more precisely you want to know the particle's location, the shorter the wavelength of the photon you need to use, and shorter wavelength photons carry more momentum. So the more precisely you determine position, the more you disturb momentum. But it goes deeper than this. The uncertainty principle isn't just about the practical difficulties of measurement, it reflects something fundamental about the nature of information and reality. Even if you could somehow measure a particle without disturbing it, the uncertainty principle would still apply because it arises from the wave nature of matter itself. A wave that's perfectly localized in position necessarily contains a broad range of wavelengths, and therefore a broad range of momenta. A wave with a precise momentum necessarily extends over a large region of space. At the scales we encounter in daily life, these quantum effects are utterly negligible. The uncertainty in the position and momentum of a bowling ball is far smaller than anything we could ever detect, even with the most sensitive instruments imaginable. The quantum world only reveals itself when we probe systems that are small enough or isolated enough for Planck's constant to matter. But for particles like electrons, the uncertainty principle becomes the dominant factor in determining their behavior. This uncertainty isn't just philosophical speculation, it has profound practical consequences. The fact that electrons can't be pinned down to exact locations is what keeps atoms stable. If electrons could settle into the lowest possible energy states with perfect precision, they would spiral into the nucleus and all matter would collapse. Instead, the uncertainty principle provides a kind of quantum pressure that maintains the structure of atoms and, by extension, everything made of atoms. The mystery deepens when we consider what happens during the process of measurement itself. Before you measure a quantum particle, it exists in that strange superposition state, with all possibilities coexisting according to the wave function. The moment you measure it, something remarkable happens that physicists call wave function collapse. The superposition suddenly disappears and the particle manifests with definite properties. This collapse isn't gradual or progressive, it's instantaneous and complete. But here's where things get truly bizarre. The particle doesn't just randomly choose one of its possible states when measured according to some hidden internal mechanism. The process of collapse seems to depend on the very act of observation itself, though what constitutes an observation remains one of the deepest puzzles in quantum mechanics. This led to famous thought experiments like Schrödinger's cat, where a quantum system is linked to a macroscopic outcome. In Schrödinger's thought experiment, a cat is placed in a sealed box with a Geiger counter, a radioactive atom, a hammer, and a flask of poison. The radioactive atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects the radiation, triggers the hammer, breaks the flask, and kills the cat. If it doesn't decay, the cat remains alive. According to the mathematics of quantum mechanics, before anyone opens the box, the radioactive atom exists in a superposition of decayed and not decayed states, which means the cat should exist in a superposition of alive and dead states. Most physicists don't believe cats can actually exist in such superposition states, but the thought experiment highlights a genuine puzzle about where exactly the quantum world ends and the classical world begins. At what point does a quantum superposition collapse into definite classical states? Is it when the radioactive atom interacts with the Geiger counter? When the Geiger counter triggers the hammer? When the poison kills the cat? Or only when a conscious observer opens the box? The boundary between quantum and classical behavior, sometimes called the quantum classical transition, remains one of the most actively researched areas in modern physics. Some theories suggest that large, complex systems naturally lose their quantum coherence through interactions with their environment, a process called decoherence. Others propose that consciousness plays a fundamental role in collapsing wave functions. Still others suggest that all possible outcomes actually occur, but in separate parallel universes that branch off at each quantum measurement. Modern experiments have confirmed these quantum predictions with extraordinary precision. Scientists can now manipulate individual atoms and photons, creating quantum superpositions and observing their collapse in real time. They've demonstrated that particles can indeed exist in multiple states simultaneously, and that the act of measurement truly does cause the wave function to collapse into a single definite outcome, these experiments have moved quantum mechanics from the realm of theoretical speculation into practical technology that's beginning to transform our world. Perhaps even stranger than superposition is the phenomenon of quantum entanglement, which Einstein famously derided as spooky action at a distance. When two particles become entangled, their quantum states become correlated in such a way that measuring one particle instantly affects the state of the other, no matter how far apart they are. This isn't communication in the usual sense. No information travels between the particles faster than light. Instead, they share a single quantum state that encompasses both particles as an inseparable whole. The creation of entangled particles typically involves starting with a single quantum system, and then splitting it in such a way that certain properties are preserved. For example, if a particle with zero spin breaks apart into two particles, conservation of angular momentum requires that the two daughter particles have opposite spins. But in the quantum world, if we haven't measured the spins, both particles exist in superpositions of spinning up and spinning down. They're entangled in such a way that if we measure one particle and find it spinning up, we instantly know that the other particle must be spinning down, even if it's on the other side of the galaxy. The strangest aspect of entanglement is that this correlation exists even though neither particle has a definite spin until the moment of measurement. It's not as if one particle was spinning up and the other was spinning down all along, and we simply didn't know which was which. The correlations that show up in entanglement experiments are stronger than anything that could exist if the particles had definite properties before measurement. This was proven definitively by John Stuart Bell in the 1960s, who showed that any theory based on local hidden variables would produce correlations that are weaker than those predicted by quantum mechanics. Bell's theorem led to a series of experiments, beginning with Alain Aspect's groundbreaking work in the 1980s that confirmed quantum mechanics and ruled out local hidden variable theories. These experiments, which earned Aspect the Nobel Prize in Physics in 2022, demonstrated that the correlations between entangled particles are indeed as strong as quantum mechanics predicts, confirming that the universe is fundamentally non-local in ways that Einstein never accepted. Recent experiments at the Large Hadron Collider have observed quantum entanglement between the heaviest known fundamental particles, top quarks, and their antimatter partners. These particles exist for only about 5 times 10 to the minus 25 seconds before decaying into other particles, yet during their brief existence they maintain quantum correlations across distances that light cannot traverse in the time available. This confirms that entanglement is not limited to light particles or stable matter, but is a universal feature of quantum mechanics that operates even in the most extreme conditions we can create. The ATLAS and CMS collaborations at CERN selected pairs of top quarks from proton-proton collisions at 13 tera-electron volts, focusing on pairs produced with low relative momentum, where quantum correlations should be strongest. By measuring the angular distributions of the particles produced when the top quarks decay, they were able to demonstrate entanglement with statistical significance exceeding 5 standard deviations, the gold standard for discovery in particle physics. Scientists in South Korea have demonstrated what they call quantitative complementarity, showing that wave and particle characteristics exist in a precise mathematical relationship. When one aspect becomes more pronounced, the other becomes correspondingly weaker, following equations that can be measured and verified with extraordinary precision. This work has closed a long-standing gap in our experimental confirmation of quantum theory's most counterintuitive predictions, providing quantitative tests of concepts that were previously more qualitative. Even more remarkably, researchers have begun to separate the wave and particle attributes of single photons, using techniques inspired by the quantum Cheshire cat concept. Just as Lewis Carroll's fictional cat could leave its grin behind when its body disappeared, quantum particles can have their wave and particle properties separated and detected in different locations. This challenges even our basic assumptions about the inseparability of an object and its properties, suggesting that the quantum world operates according to principles that are even stranger than we previously imagined. These quantum Cheshire cat experiments use weak measurements, a technique that allows researchers to extract information about a quantum system without completely collapsing its wave function. By applying weak disturbances to photons in carefully designed interferometers, scientists can separate where the photon is detected, its particle aspect, from where it creates interference patterns, its wave aspect. This separation occurs in a regime of imaginary time evolution, where the usual rules of quantum mechanics are extended into mathematical territories that have no classical analogue. The practical applications of quantum mechanics have already transformed our world in ways most people never realize. The electronic devices that surround us all function according to quantum principles. Semiconductors work because electrons in crystalline materials form energy bands separated by forbidden gaps, a purely quantum mechanical effect. The transistors that make computers possible rely on quantum tunneling, the ability of electrons to pass through energy barriers that classical physics says should be impenetrable. Lasers operate by stimulated emission, a process where photons encourage atoms to emit additional photons with identical properties, creating coherent beams of light with precisely defined wavelength and phase. Magnetic resonance imaging uses the quantum mechanical property of nuclear spin to create detailed images of the human body without harmful radiation. The global positioning system depends on atomic clocks that use quantum transitions in cesium atoms to maintain time with extraordinary precision. But we're only beginning to harness the full potential of quantum mechanics. Quantum computers promise to solve certain problems exponentially faster than any classical computer could manage. Instead of storing information in bits that are either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in superpositions of both states simultaneously. This allows quantum computers to explore multiple solution paths in parallel, potentially revolutionizing everything from drug discovery to financial modeling to artificial intelligence. The challenge in building quantum computers lies in maintaining quantum coherence long enough to perform useful calculations. Quantum states are incredibly fragile and easily disturbed by interactions with the environment. Even the smallest amount of noise can cause decoherence, destroying the superpositions and entanglement that quantum computers need to function. Researchers have developed sophisticated error correction codes that can protect quantum information by spreading it across multiple physical qubits and continuously monitoring for errors without directly measuring the quantum states. Recent advances have led to quantum computers with hundreds of qubits that can maintain coherence for milliseconds, long enough to perform meaningful calculations. IBM has announced plans for quantum computers with over 100,000 qubits by the end of this decade, potentially powerful enough to solve problems that are completely intractable for classical computers. These machines could simulate complex molecular systems for drug development, optimize financial portfolios in ways that account for quantum fluctuations in market behavior, or break the cryptographic codes that currently protect digital communications. Quantum cryptography uses the principles of quantum entanglement and the no-cloning theorem to create communication systems that are fundamentally secure. Any attempt to eavesdrop on a quantum encrypted message necessarily disturbs the quantum states involved, alerting the intended recipients to the presence of an intruder. This security doesn't depend on the computational difficulty of mathematical problems, as current encryption schemes do, but on the fundamental laws of physics themselves. Several countries are already building quantum communication networks that span hundreds of kilometers. China has deployed a quantum communication satellite that can distribute entangled photons between ground stations separated by thousands of kilometers. The European Union has launched a quantum internet initiative aimed at connecting quantum computers and sensors across the continent. In the United States, the Department of Energy is developing a quantum internet that will connect national laboratories and universities in a secure quantum network. Quantum sensors can detect changes in gravitational fields, magnetic fields, electric fields, and other physical properties with unprecedented precision. These devices use quantum superposition and entanglement to amplify tiny signals that would be impossible to detect with classical sensors. Quantum magnetometers can detect magnetic fields so weak they would be completely overwhelmed by thermal noise in classical devices. Quantum accelerometers can measure accelerations with precision that approaches the fundamental limits imposed by quantum mechanics itself. These quantum sensors may eventually allow us to see inside the human body without harmful radiation, detect underground resources like oil or precious metals, monitor the structural integrity of buildings and bridges, or even probe the fundamental structure of space and time itself. Gravitational wave detectors like LIGO already use quantum techniques to detect ripples in space-time caused by colliding black holes and neutron stars. Future generations of these detectors will use quantum squeezing and other techniques to push sensitivity to the quantum limit. The history of quantum mechanics is filled with brilliant insights, emerging from careful attention to experimental anomalies and theoretical puzzles. Max Planck's investigation of black body radiation in 1900 led him to propose that energy comes in discrete packets, or quanta, rather than being continuously variable as classical physics assumed. This was the first crack in the edifice of classical physics, though Planck himself initially viewed it as merely a mathematical convenience rather than a fundamental truth about nature. Planck was studying the spectrum of light emitted by hot objects, trying to understand why classical physics predicted that hot objects should emit infinite amounts of ultraviolet radiation, a prediction that was obviously wrong. By assuming that electromagnetic energy could only be absorbed or emitted in discrete chunks, proportional to the frequency of the radiation, Planck was able to derive the correct formula for black body radiation. But he thought this quantization was just a mathematical trick that would eventually be eliminated when the correct classical theory was developed. Einstein's Nobel Prize-winning explanation of the photoelectric effect built on Planck's work and firmly established the quantum nature of electromagnetic radiation. But Einstein never became comfortable with the probabilistic interpretation of quantum mechanics that emerged from these discoveries. His famous declaration that God does not play dice with the universe reflected his belief that there must be some deeper, deterministic reality underlying the quantum randomness we observe. Einstein spent the last decades of his life searching for a unified field theory that would restore determinism to physics, but he never found the hidden variables he was looking for. The Copenhagen interpretation of quantum mechanics, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s and 30s, suggested that quantum systems don't have definite properties independent of measurement. According to this view, the wave function doesn't describe some underlying reality that exists whether we observe it or not, but rather encodes our knowledge about the system and the probabilities for different measurement outcomes. The act of measurement doesn't reveal pre-existing properties, but actually creates them, bringing specific aspects of reality into existence through the process of observation. This interpretation sparked decades of debate about the nature of reality itself. Does the moon exist when nobody is looking at it? Einstein asked mockingly, highlighting what seemed to him the absurd implications of the Copenhagen interpretation. The question isn't as silly as it sounds. If quantum mechanics applies to everything in the universe, then in some sense the moon should exist in a superposition of all possible states until someone observes it and causes the wave function to collapse. The fact that this seems absurd for macroscopic objects like the moon points to deep questions about where and why quantum effects give way to classical behavior. Many alternative interpretations have been proposed over the years, each trying to make sense of quantum mechanics without abandoning our intuitions about the nature of reality. The many worlds interpretation, developed by Hugh Everett III in the 1950s, suggests that every quantum measurement causes the universe to split into multiple parallel realities, each corresponding to a different measurement outcome. In this view, Schrödinger's cat is both alive and dead, but in separate universes that can never communicate with each other. Every time a quantum measurement occurs, the universe branches into multiple copies, creating a vast multiverse of parallel realities. The de Broglie-Bohm theory, also known as pilot wave theory, proposes that particles do have definite positions and velocities at all times, but their motion is guided by a quantum field called the pilot wave that we cannot directly observe. This hidden variable theory reproduces all the predictions of standard quantum mechanics while maintaining a deterministic picture of reality underneath the quantum randomness. The apparent randomness of quantum measurements arises from our ignorance of the initial conditions, not from fundamental indeterminacy in nature itself. The spontaneous collapse theories suggest that wave function collapse is a real physical process that occurs spontaneously, without the need for conscious observation or interaction with measuring apparatus. These theories propose that the wave function undergoes random, spontaneous localizations at a rate that's negligible for individual particles, but becomes significant for large, complex systems. This would explain why macroscopic objects like cats appear to have definite properties while microscopic systems remain in quantum superposition. These interpretations make identical predictions for the outcomes of experiments, so there may be no way to determine experimentally which, if any, correctly describes the ultimate nature of reality. What matters for practical purposes is that the mathematical formalism of quantum mechanics works with extraordinary precision. When physicists calculate the magnetic moment of an electron using quantum electrodynamics, their answer agrees with experimental measurements to better than 1 part in a trillion, making it the most precisely verified prediction in all of science. The quantum world reveals itself most clearly in the realm of the very small, but its influence extends throughout the universe in ways that are often subtle but always profound. The fusion reactions that power stars depend on quantum tunneling, a process that allows nuclei to overcome the electromagnetic repulsion between protons and fuse together to form heavier elements. Without quantum tunneling, the cores of stars would never get hot enough to sustain fusion reactions, the sun would not shine, and life on Earth would be impossible. Classical physics predicts that the protons in stellar cores don't have nearly enough energy to overcome the electromagnetic barrier that keeps atomic nuclei apart. The temperature at the center of the Sun is about 15 million Kelvin, which gives protons an average kinetic energy of about 1,000 electron volts. But the electromagnetic barrier between protons has a height of roughly 1 million electron volts, 1,000 times higher than the typical proton energy. Classical physics would predict that fusion should be impossible under these conditions. Quantum mechanics changes everything. The wave nature of matter means that particles don't have to go over energy barriers, they can tunnel through them. The probability of tunneling decreases exponentially with the height and width of the barrier, but it never becomes exactly zero. Even though most protons in stellar cores don't have enough energy to overcome the electromagnetic barrier, a small fraction can tunnel through and fuse with other nuclei. This tiny tunneling probability is enough to sustain the fusion reactions that power stars and create the heavy elements necessary for life. The structure of matter itself emerges from quantum principles in ways that have no classical analogue. The reason different elements have different chemical properties comes down to the quantum mechanical behavior of electrons in atoms. The shapes of electron orbitals, the discrete energy levels that electrons can occupy, the rules that govern chemical bonding, all of these arise from the solutions to Schrödinger's equation for electrons moving in the electric fields created by atomic nuclei. The Pauli exclusion principle, which states that no two electrons can occupy exactly the same quantum state, is responsible for the periodic table of elements and the diversity of chemical behavior we observe. If electrons were classical particles, they would all settle into the lowest energy orbital around each nucleus, and all atoms would be essentially identical. Instead, electrons are forced into higher and higher energy levels as atoms get larger, creating the complex electronic structures that give different elements their unique properties. Even the stability of ordinary matter depends on quantum effects in ways that weren't fully appreciated until the development of quantum mechanics. Classical electrodynamics predicts that electrons orbiting atomic nuclei should spiral inward and collapse within a tiny fraction of a second, radiating away their energy as electromagnetic waves according to Larmore's formula. The fact that atoms are stable requires quantum mechanics, specifically the quantization of electron energy levels that prevents them from settling into forbidden states below the ground state. The quantum nature of electrons also explains why matter has the mechanical properties we observe. The rigidity of solids, the incompressibility of liquids, the resistance of materials to deformation, all of these emerge from the quantum mechanical repulsion between electrons as they are forced into higher energy states when atoms are pushed together. This quantum pressure, arising ultimately from the uncertainty principle and the Pauli exclusion principle, is what gives matter its structural integrity. On cosmic scales, quantum mechanics played a crucial role in shaping the universe we see today. In the earliest moments after the Big Bang, when the universe was smaller than a subatomic particle, tiny quantum fluctuations in the density of matter and energy were stretched to astronomical proportions by cosmic inflation. These quantum fluctuations became the seeds around which galaxies and galaxy clusters eventually formed billions of years later. The cosmic microwave background radiation that fills all of space carries the imprint of these primordial, quantum variations. The tiny temperature differences observed by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory represent quantum fluctuations that occurred when the universe was only a fraction of a second old. These measurements provide direct evidence that quantum mechanics was operating at the very beginning of time and space, shaping the large-scale structure of the cosmos. Current research in quantum physics continues to reveal new surprises and applications that push the boundaries of what we thought possible. Scientists are exploring quantum materials that exhibit exotic properties like high-temperature superconductivity, where electrical current can flow without resistance at temperatures that can be maintained with liquid nitrogen rather than liquid helium. These materials could revolutionize power transmission, magnetic levitation systems, and energy storage in ways that could transform our technological civilization. Topological quantum materials possess properties that are protected against environmental disturbance by deep mathematical principles related to the global structure of their quantum states. These materials can maintain their quantum properties even in the presence of impurities, defects, and thermal fluctuations that would destroy conventional quantum states. Topological insulators conduct electricity on their surfaces while remaining insulating in their bulk, creating new possibilities for quantum electronics and spintronics. Quantum error correction, a field that barely existed 20 years ago, now provides sophisticated methods for protecting quantum information against the inevitable noise and interference that plague quantum systems. These techniques make it possible to build large-scale quantum computers that maintain their quantum properties even in the presence of imperfections and environmental disturbance. By encoding quantum information redundantly across multiple physical qubits and continuously monitoring for errors without directly measuring the quantum states, researchers can extend quantum coherence times indefinitely in principle. Recent experiments have pushed the boundaries of quantum mechanics into new regimes that test our understanding of the quantum classical boundary. Physicists have created quantum superpositions of increasingly large objects, from individual atoms to small molecules containing hundreds of atoms, to microscopic mechanical oscillators that are visible under an optical microscope. Each new milestone brings us closer to understanding whether the quantum classical transition is a fundamental feature of nature or simply a practical limitation of our current technology. The field of quantum biology has emerged as scientists discover quantum effects in living systems that have been shaped by billions of years of evolution. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to use quantum superposition and entanglement to transfer energy with nearly perfect efficiency from light harvesting complexes to reaction centers. The quantum coherence allows energy to explore multiple pathways simultaneously and find the most efficient route to its destination. Some species of birds may navigate during migration using quantum entanglement in cryptochrome proteins in their eyes, allowing them to literally see magnetic fields as patterns of light and shadow overlaid on their visual field. The Earth's magnetic field affects the quantum states of electron pairs in these proteins, creating a kind of quantum compass that could explain how birds can navigate with extraordinary precision across thousands of miles of open ocean. Even the sense of smell might involve quantum mechanical processes that allow odorant molecules to be identified by their vibrational frequencies rather than just their shapes. The quantum tunneling of electrons in olfactory receptors could provide a mechanism for distinguishing between molecules that have the same shape but different vibrational modes, explaining why molecules with similar structures can have completely different smells. These discoveries suggest that quantum mechanics isn't just relevant to sterile laboratory conditions or exotic materials at ultra-low temperatures, but plays a role in the warm, wet, noisy environment of living cells. Evolution, it seems, has found ways to exploit quantum effects for biological advantage, opening up entirely new possibilities for biomimetic technologies that could surpass anything we can currently build with purely classical engineering. Looking toward the future, quantum physics promises to revolutionize our understanding of fundamental questions about the nature of time, space, gravity, and information. Quantum field theory, which combines quantum mechanics with special relativity, has revealed deep connections between seemingly unrelated phenomena across vast ranges of energy and distance. The same mathematical structures that describe the behavior of elementary particles also appear in condensed matter systems, black hole physics, and cosmological models. String theory and loop quantum gravity, two approaches to developing a quantum theory of gravity, predict that space and time themselves have a granular structure at the smallest scales imaginable. If these theories are correct, then the smooth spacetime of Einstein's general relativity is only an approximation that breaks down when we probe distances smaller than the Planck length, about 10 to the minus 35 meters, and time intervals shorter than the Planck time, about 10 to the minus 43 seconds. At these scales, quantum fluctuations in the geometry of spacetime itself become significant. Virtual particles pop in and out of existence, borrowing energy from the vacuum and paying it back before the uncertainty principle notices. The vacuum isn't empty at all, but seethes with quantum activity that has measurable effects on the properties of real particles. The Casimir effect, where two metal plates in vacuum attract each other due to quantum fluctuations, demonstrates that these virtual particles are more than just mathematical abstractions. Quantum information theory has revealed fundamental connections between information, energy, entropy, and the structure of space-time that were never anticipated by the founders of quantum mechanics. The process of erasing information, it turns out, requires energy and produces heat according to Landauer's principle, linking computation to thermodynamics in ways that have profound implications for the ultimate limits of computing and the nature of physical reality. Black holes, the most extreme objects in the universe, appear to be quantum information processing systems that store information on their event horizons and radiate it back out through Hawking radiation. The information paradox, which asks what happens to information that falls into a black hole, has led to new insights about the relationship between quantum mechanics and gravity. Some theories suggest that the information is never truly lost, but is encoded in subtle correlations in the Hawking radiation, while others propose that black holes are actually firewalls that destroy information in fundamental violation of quantum mechanics. The holographic principle, inspired by black hole physics, suggests that all the information in a volume of space can be encoded on its boundary, just as a hologram encodes three-dimensional information on a two-dimensional surface. This principle has led to remarkable developments in both theoretical physics and quantum information, including the ADES-CFT correspondence that relates quantum field theories to theories of gravity in higher dimensions. The measurement problem in quantum mechanics, the question of how and why wave function collapse occurs, remains one of the deepest unsolved puzzles in all of science. Despite decades of theoretical work and increasingly sophisticated experiments, we still don't understand the precise mechanism by which the quantum realm of superposition and entanglement gives way to the classical world of definite outcomes. Some physicists believe the answer lies in modifications to quantum mechanics that become apparent at large scales, while others think the solution requires a completely new understanding of the relationship between consciousness, information, and physical reality. Recent experiments have probed the measurement process with unprecedented precision, using techniques like weak measurement and quantum non-demolition measurements to extract information about quantum systems without completely destroying their coherence. These studies have revealed that the transition from quantum to classical behavior is more subtle and gradual than the simple wave function collapse picture suggests, involving complex interactions between the measured system, the measuring apparatus, and the environment. The development of quantum technologies is also revealing new aspects of fundamental physics. Quantum computers operating at the edge of their capabilities sometimes exhibit behavior that doesn't match our current understanding of quantum decoherence. Quantum sensors approaching the standard quantum limit are uncovering discrepancies in our models of how quantum systems interact with electromagnetic fields and gravitational waves. These technological advances are pushing us into regimes where quantum mechanics meets other areas of physics in ways that were previously impossible to explore experimentally. Quantum optomechanics, which studies the interaction between light and mechanical motion at the quantum level, is revealing connections between quantum mechanics and general relativity. Experiments with quantum systems in strong gravitational fields may eventually test whether gravity itself is quantum mechanical or remains fundamentally classical. The philosophical implications of quantum mechanics continue to challenge our most basic assumptions about the nature of reality, causality, and the role of observation in determining what exists. The delayed choice quantum eraser experiments show that the decision of whether to observe which path information can apparently be made after a photon has already passed through a double slit, raising profound questions about the nature of time and causation in quantum mechanics. Quantum teleportation, the process of transferring quantum states from one location to another using entanglement and classical communication, demonstrates that quantum information has properties that are fundamentally different from classical information. The no-cloning theorem proves that quantum information cannot be copied perfectly, while quantum entanglement allows correlations that are stronger than anything possible in classical physics. These discoveries are reshaping our understanding of what information actually is and how it relates to physical reality. The emerging field of quantum thermodynamics is exploring how the laws of thermodynamics need to be modified when applied to quantum systems that are small enough for quantum effects to dominate. Traditional thermodynamics assumes that systems can be characterized by well-defined properties like temperature and entropy, but quantum systems in superposition states can exhibit thermodynamic behaviors that have no classical analog. Quantum heat engines can operate more efficiently than their classical counterparts by exploiting quantum coherence and entanglement. Quantum refrigerators can cool systems to temperatures below what classical thermodynamics would allow. These quantum thermal machines may eventually find applications in quantum computing, where managing heat and entropy at the quantum level is crucial for maintaining coherence. The study of quantum phase transitions, where quantum systems undergo sudden changes in their ground state properties as external parameters are varied, has revealed universal principles that apply across vastly different physical systems. The same mathematical descriptions that govern quantum magnets also apply to ultra-cold atomic gases, quantum dots, and even certain aspects of black hole physics. These universality principles suggest that quantum mechanics contains deep organizing principles that transcend the specific details of particular physical systems. The emergence of classical behavior from quantum foundations, the role of entanglement in phase transitions, and the relationship between quantum information and thermodynamics all point toward a more unified understanding of how quantum mechanics shapes the physical world at every scale. As we push further into the quantum realm, we're discovering that nature is even stranger and more wonderful than the pioneers of quantum mechanics could have imagined. Quantum systems exhibit behaviors that challenge not just our intuitions about how the world should work, but our very concepts of what it means for something to exist or to have properties. The quantum world operates according to its own logic, one that is simultaneously mathematical and mystical, precise and paradoxical. Yet from this apparent chaos of quantum uncertainty emerges the ordered, predictable world of classical physics that we experience every day. The challenge for future generations of physicists will be to understand how this emergence occurs, not just as a mathematical approximation, but as a fundamental aspect of how reality is structured. We need to understand why the universe appears classical at large scales while remaining quantum at small scales, and whether this division is absolute or simply a limitation of our current perspective. The practical applications of quantum mechanics will continue to transform human civilization in ways we can barely imagine. Quantum computers may eventually simulate complex systems like the human brain or the climate in ways that reveal new principles of organization and control. Quantum sensors may detect gravitational waves from the Big Bang itself, or discover new fundamental particles that exist only in the quantum vacuum. Quantum communication networks may create a new kind of internet where information is protected by the laws of physics themselves. But perhaps the most profound impact of quantum mechanics will be on our understanding of ourselves and our place in the cosmos. If consciousness plays a fundamental role in quantum measurement, then the dividing line between observer and observed, between mind and matter, may be far more subtle than we have assumed. The quantum world suggests that reality is not simply out there waiting to be discovered, but is in some sense created through the process of observation and interaction. The story of quantum mechanics is ultimately a story about the deepest mysteries of existence itself. It tells us that the universe is not a clockwork mechanism operating according to predetermined laws, but something far stranger and more creative. It's a realm where possibilities exist alongside actualities, where the future can influence the past, where separated parts remain connected in ways that transcend space and time. As we continue to explore these quantum foundations, We're not just uncovering abstract truths about the behavior of subatomic particles, we're discovering new ways to think about information, reality, and consciousness itself. We're learning that the universe is far more interconnected and interdependent than classical physics ever suggested, bound together by quantum correlations that link every part to every other part in an invisible web of relationship. The quantum revolution has already transformed our understanding of matter, energy, space, and time. But we are still in the early stages of learning how to think quantum mechanically, how to develop intuitions that match the strange logic of the quantum world. Future generations may look back on our current understanding as quaint and limited, just as we now view the classical physics that preceded quantum mechanics. What remains constant is the sense of wonder and mystery that quantum mechanics brings to our understanding of nature. Every new discovery reveals new puzzles. Every answered question opens up new areas of exploration. The quantum world is not just a subject for scientific study, it's a source of endless fascination that reminds us how much we still have to learn about the universe and our place within it. The mathematics of quantum mechanics provides precise predictions for experimental outcomes, but the meaning of those equations continues to evolve as we discover new aspects of quantum reality. We're still learning the language of the quantum world, still developing the conceptual tools needed to think clearly about superposition, entanglement, and measurement. Each generation of physicists brings new insights and new questions to this eternal conversation between human curiosity and the deep structures of reality. In the end, quantum mechanics teaches us humility in the face of nature's complexity and creativity. It shows us that the universe operates according to principles that transcend our everyday experience and challenge our most basic assumptions about how things ought to work. Yet it also demonstrates the power of human reason and imagination to penetrate even the strangest mysteries, to find mathematical order in apparent chaos, and to transform our understanding of reality through careful observation and creative theoretical insight. This brings us to explore how these quantum principles manifest in the most intimate processes of life itself, where billions of years of evolution have discovered quantum solutions that human technology is only now beginning to appreciate, revealing connections between the fundamental physics of matter and the emergence of consciousness, complexity, and the extraordinary phenomenon we call living systems. In the quiet moments before dawn on September 14th, 2015, something extraordinary rippled through the very fabric of our universe. Two black holes, each dozens of times more massive than our Sun, completed a cosmic dance that had been unfolding for billions of years. In their final moments together, they spiraled closer and closer until they collided with unimaginable violence. The energy released in that collision was 50 times greater than the light from every star in the visible universe combined. Think about that for a moment. Yet this cataclysmic event, which occurred 1.3 billion years ago, reached us not as light or radio waves, but as something far more fundamental, something that Albert Einstein had predicted but doubted we would ever detect. It came to us as ripples in space-time itself, stretching and compressing the very dimensions of reality by less than 1,000th the width of a proton across a distance of thousands of kilometers. This detection by the Laser Interferometer Gravitational Wave Observatory marked not just a triumph of human ingenuity, but a moment when we finally touched the deepest truth about our universe. Space and time are not the fixed stage upon which cosmic dramas unfold. They are the drama itself, a dynamic, flowing, four-dimensional tapestry that bends and waves and carries within its geometry the story of everything that has ever been. The journey to this profound realization began in the most mundane of circumstances. In 1905, a 26-year-old patent clerk in Bern, Switzerland, was pondering a problem that had been troubling physicists for decades. Albert Einstein spent his days evaluating patent applications for electromagnetic devices, but his mind wandered to deeper questions about the nature of light and motion. The equations of electromagnetic theory, crafted by James Clerk Maxwell decades earlier, contained a curious prediction. Light should always travel at the same speed through empty space, roughly 300 million meters per second, regardless of how the source or observer might be moving. This seemed to contradict everything we know about motion. When you throw a ball from a moving train, Its speed relative to the ground is the sum of your throwing speed and the trained speed. When you run toward an oncoming car, it appears to approach you faster than if you stood still. Yet Maxwell's equations suggested that light behaved differently. A beam of light emitted from a speeding spaceship should still be measured at exactly the same speed by any observer, whether they were rushing toward the source or fleeing from it. Einstein's genius was to take this apparent contradiction and embrace it as a fundamental truth about reality. What if light's constant speed was not a quirk of electromagnetic theory, but a basic law of nature? What if the problem lay not with light, but with our assumptions about space and time themselves? The implications were staggering. If light always travels at the same speed, then something else must be flexible to accommodate this constancy. That something, Einstein realized, was space-time itself. Space and time could no longer be thought of as separate, absolute entities as Newton had conceived them. Instead, they were relative, intimately connected, and dependent entirely on the observer's state of motion. Consider two observers, Alice and Bob. Alice is sitting quietly in a chair, while Bob rockets past her at 90% the speed of light. From Alice's perspective, Bob's clocks run slowly, his rulers are contracted, and time itself seems stretched in his rapidly moving frame. But from Bob's perspective, he is at rest, and Alice is the one moving backward at 90% light speed. Her clocks run slowly, her rulers contract. Each observer sees the other's time dilated and space contracted, yet neither can claim to be truly at rest. Motion is relative, but the speed of light remains the same for both. This symmetry breaks only when one observer accelerates. If Bob turns around and comes back to Alice, he will find that less time has passed for him than for her. This is not science fiction but established fact, confirmed in countless experiments. Atomic clocks flown on airplanes return running slow compared to identical clocks left on the ground. Particles created in cosmic ray showers high in the atmosphere live long enough to reach Earth's surface only because time dilation allows their normally brief lifespans to stretch from their perspective. Einstein's breakthrough came from recognizing that space and time are not separate entities, but aspects of a single four-dimensional continuum. Hermann Minkowski, Einstein's former mathematics professor, captured this insight with startling clarity. In 1908, Minkowski declared that space by itself and time by itself were doomed to fade into shadows, and only a union of the two would preserve an independent reality. In Minkowski's mathematical framework, every event in the universe can be described by four coordinates, 3 for space and 1 for time. Your entire life traces out a path through this four-dimensional space-time, a trajectory physicists call your world line. The world line of a photon, a particle of light, cuts through space-time at a 45-degree angle when drawn on a space-time diagram, representing its maximum possible speed through space as time progresses. But Einstein's insights had only just begun. His special theory of relativity revealed the deep connection between space, time, and uniform motion, but it could not address acceleration or gravity. These phenomena required a more profound revolution in our understanding of reality itself. The key insight came to Einstein during what he called the happiest thought of his life. In 1907, while sitting in his chair at the patent office, he imagined what it would feel like to fall freely from the roof of a house. In that moment of weightless freefall, Einstein realized, you would feel no gravity at all. You and any objects falling beside you would float relative to each other, just as if you were drifting in the weightless environment of deep space. Conversely, Einstein reasoned, if you were trapped inside a windowless elevator being accelerated upward by some external force, the floor would press against your feet with exactly the same sensation as gravity pulling you downward. You could perform no experiment inside that elevator to determine whether you were being accelerated upward in empty space or sitting at rest in a gravitational field. This equivalence principle, as Einstein called it, suggested something remarkable. Gravity and acceleration are not merely similar phenomena, they're identical, two different descriptions of the same underlying reality. But what could this reality be? Einstein's answer revolutionized our understanding of space and time themselves. Massive objects, he proposed, do not exert gravitational forces across empty space in the manner Newton had imagined. Instead, they warp the very geometry of space-time. Picture spacetime as a vast, flexible membrane stretched taut in 4 dimensions. Place a massive object like the Sun upon this membrane, and it creates a depression, a curvature in the fabric of reality itself. Now imagine a planet like Earth moving through this curved spacetime. It does not feel any force pulling it toward the Sun. Rather, it follows the straightest possible path through the curved geometry created by the Sun's mass. From Earth's perspective, it is travelling in a straight line through space-time, but that line curves through space as it progresses through time, creating what we perceive as an orbital motion. This is Einstein's general theory of relativity, published in 1915 after a decade of intense mathematical struggle. The theory describes gravity not as a force between masses, but as the curvature of space-time itself. In Einstein's elegant summary, matter tells space-time how to curve, and curved space-time tells matter how to move. The mathematical language required to express these ideas was formidable. Einstein needed the tools of differential geometry and tensor calculus to describe how space-time could curve in 4 dimensions, while preserving the fundamental symmetries of physics. His field equations relate the curvature of space-time at every point to the density of mass and energy at that point. These equations are non-linear and extraordinarily difficult to solve, yet they have provided some of the most precise and successful predictions in all of physics. Within months of publishing his theory, Einstein made several predictions that could be tested. The planet Mercury, closest to the Sun, should experience the strongest effects of space-time curvature. Einstein calculated that Mercury's elliptical orbit should slowly rotate or precess by 43 arcseconds per century beyond what Newtonian gravity would predict. When astronomers checked their records, they found that Mercury's orbit was indeed precessing by exactly this amount, a discrepancy that had puzzled them for decades. Even more dramatically, Einstein predicted that light itself should follow the curved paths of space-time. A beam of light passing close to the Sun should be deflected by twice the amount that Newton's gravity would suggest. This prediction could be tested during a solar eclipse, when stars normally hidden by the Sun's glare would become visible. If Einstein was correct, these stars should appear slightly displaced from their usual positions. On May 29, 1919, British astronomer Arthur Eddington led expeditions to observe a total solar eclipse from the island of Principe off the coast of Africa and from Sobral in Brazil. When they measured the positions of stars near the eclipsed Sun, they found exactly the deflection Einstein had predicted. The announcement of this confirmation made Einstein an international celebrity overnight and marked a watershed moment in the history of science. But general relativity's most profound predictions were yet to be tested. Einstein's equations naturally gave rise to solutions describing objects so massive and compact that they would curve space-time to its breaking point. In 1916, just months after Einstein published his theory, German physicist Karl Schwarzschild found a solution describing the space-time around a spherically symmetric mass. The Schwarzschild solution revealed something extraordinary. For any given mass, there exists a critical radius where the curvature of space-time becomes so extreme that nothing, not even light, can escape. This radius, now called the Schwarzschild radius or event horizon, defines the boundary of a black hole. For an object with the mass of our Sun, this critical radius is about 3 kilometers. For Earth, it would be less than 1 centimeter. The concept of black holes seemed so bizarre that even Einstein himself was skeptical they could exist in nature. These would be regions of space-time so severely warped that they would be cut off from the rest of the universe. Anything crossing the event horizon would be doomed to fall toward the central singularity, a point where the curvature becomes infinite and our current understanding of physics breaks down completely. Yet, as astronomers developed more powerful instruments throughout the 20th century, they began finding indirect evidence for these exotic objects. Stars in binary systems sometimes orbit invisible companions so massive that they could only be black holes. X-ray telescopes revealed hot gas spiraling into what appeared to be infinitely deep gravitational wells. Radio telescopes detected jets of matter travelling at nearly the speed of light, seemingly launched from the vicinity of supermassive black holes at the centres of distant galaxies. Einstein's theory also predicted another exotic phenomenon that seemed equally unlikely to be detected. Just as accelerating electric charges produce electromagnetic waves, Einstein showed that accelerating masses should produce waves in space-time itself. These gravitational waves would travel at the speed of light, carrying energy away from their sources and causing tiny periodic stretches and compressions in the fabric of space. Einstein calculated that even the most violent cosmic events would produce gravitational waves so weak they would be nearly impossible to measure. The collision of two neutron stars, for example, might change the length of a kilometre-long detector by less than 1,000th the diameter of a proton. Such measurements seemed hopelessly beyond the reach of any conceivable technology. For decades, gravitational waves remained a theoretical curiosity, a mathematically elegant consequence of Einstein's equations, but seemingly forever beyond experimental verification. Then, in the 1970s, astronomers Russell Hulse and Joseph Taylor made a discovery that changed everything. They found a pulsar, a rapidly spinning neutron star that beams radio waves toward Earth like a cosmic lighthouse, with a most unusual property. This pulsar had a companion, another neutron star, and the two were locked in a tight orbital dance. The pulsar's radio signals allowed Hulse and Taylor to track this orbit with extraordinary precision, timing the pulsar's radio pulses to within microseconds. Over several years of observations, they discovered something remarkable. The two neutron stars were slowly spiraling toward each other, losing orbital energy at precisely the rate Einstein's theory predicted they should if they were radiating gravitational waves. This was the first indirect evidence that gravitational waves actually existed, carrying energy away from the orbiting neutron stars and causing their orbit to decay. Hulse and Taylor's discovery would eventually earn them the Nobel Prize in Physics, but it also sparked dreams of detecting gravitational waves directly. The challenge was formidable. To detect the minuscule stretching and compressing of space caused by passing gravitational waves required instruments of unprecedented sensitivity. The solution came through laser interferometry, a technique that could measure incredibly small changes in distance by comparing the phases of laser beams travelling along perpendicular paths. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consisted of two identical detectors, one in Livingston, Louisiana, and another in Hanford, Washington. Each detector featured two arms 4 kilometers long arranged in an L shape. Laser light is split and sent down both arms, bouncing between mirrors at each end before recombining. Under normal circumstances, the two beams return in perfect synchronization, but a passing gravitational wave would stretch space along one arm while compressing it along the other, causing the beams to go slightly out of phase. The original LIGO detectors began operating in 2002, listening patiently to the cosmos for signs of these very elusive ripples in space-time. For over a decade, they heard nothing but noise. The instruments, though representing the pinnacle of precision measurement technology, were not quite sensitive enough to detect the faint whispers of the distant cosmic violence. Then came advanced LIGO, an ambitious upgrade that increased the detector's sensitivity by more than a factor of 10. New laser systems, improved mirror suspensions, and sophisticated vibration isolation systems transformed LIGO into the most sensitive measuring instrument ever built. The upgraded detectors could sense changes in the 4-kilometer arm length smaller than 1/10,000th the width of a proton. Advanced LIGO officially began its first observing run on September 18, 2015. But just 4 days before the official start, while the detectors were still in engineering mode, something extraordinary happened. At 9:51 Universal Time on September 14, 2015, both LIGO detectors simultaneously registered a signal unlike anything ever seen before. The signal lasted just 0.2 of a second, rising in frequency from 35 Hz to 250 Hz in a characteristic pattern called a chirp. The waveform matched Einstein's predictions with stunning precision. Two black holes, one 36 times the mass of our Sun and another 29 times as massive, had been spiraling toward each other for billions of years. In their final moments, they completed hundreds of orbits per second before merging into a single, more massive black hole. The collision released energy equivalent to 3 times the mass of our Sun, converted entirely into gravitational waves in a fraction of a second. At the moment of peak power output, these gravitational waves carried 50 times more energy than all the stars in the visible universe combined. Yet by the time these ripples reached Earth after travelling for 1.3 billion years, they had weakened to the point where they stretched space by less than the width of a proton across LIGO's 4-kilometre arms. The detection was so clear it could be seen in the raw data without any sophisticated analysis. The signal arrived at the Louisiana detector 7 milliseconds before reaching Washington, consistent with a gravitational wave travelling at the speed of light from somewhere in the southern hemisphere. The event was designated GW150914, marking the birth of gravitational wave astronomy. This first detection was just the beginning. In the years since, LIGO and its partner detectors around the world have revolutionized our understanding of the universe. They've detected dozens of black hole mergers, each one revealing new insights about these most extreme objects in nature. The observed black holes are far more massive than anyone expected, suggesting that stellar evolution in the early universe followed different pathways than previously thought. In October 2017, LIGO achieved another historic milestone by detecting the collision of 2 neutron stars. Unlike black hole mergers, which produce gravitational waves but no light, neutron star collisions create spectacular electromagnetic fireworks. The gravitational wave detection allowed astronomers to point their telescopes toward the source, witnessing the birth of heavy elements like gold and platinum in nuclear furnaces of unimaginable intensity. These multi-messenger observations have opened entirely new ways of studying the cosmos. Gravitational waves carry information about their sources that cannot be obtained through any other means. They tell us about the masses and spins of black holes, the equation of state of matter under conditions more extreme than anything we can create on Earth, and the expansion rate of the universe itself. But perhaps the most profound confirmation of Einstein's spacetime revolution came in 2019, when the Event Horizon Telescope collaboration unveiled the first image of a black hole's event horizon. This remarkable achievement required linking radio telescopes around the globe into a virtual instrument the size of Earth itself, achieving angular resolution so fine that it could read a newspaper in New York from a cafe in Paris. The target was Mazastine 87 star, the supermassive black hole at the centre of the giant elliptical galaxy Messier 87, located 55 million light-years away in the constellation Virgo. This monster contains 6.5 billion times the mass of our Sun, concentrated in a region smaller than our solar system. The image revealed exactly what Einstein's theory predicted, a dark shadow surrounded by glowing material heated to billions of degrees as it spiraled toward its doom. The shadow was perfectly circular, as general relativity requires, and measured exactly the size Einstein's equations dictated for a black hole of this mass. The bright ring surrounding the shadow was brighter on one side, caused by relativistic effects as material on the approaching side of the spinning black hole had its light boosted toward us by the Doppler effect. This image represented more than just a stunning visual confirmation of black holes' existence. It provided a direct test of general relativity in the most extreme gravitational environment accessible to observation. The black hole's immense gravity bends light around it so severely that we can see the backside of the accretion disk, light that has been lensed around the black hole's shadow like looking over its shoulder. The Event Horizon. Telescope has since imaged Sagittarius, a star, a supermassive black hole at the centre of our own Milky Way galaxy. Though much closer to us, this black hole proved more challenging to image because it is over 1,000 times less massive than 87 star. The hot gas orbiting Sagittarius, a star, completes circuits in minutes rather than days, creating a turbulent, rapidly changing environment that required new analysis techniques to reveal its secrets. These observations have allowed astronomers to test Einstein's theory in gravitational fields billions of times stronger than anything we experience on Earth. The results consistently support general relativity's predictions, but they also reveal the complex astrophysics surrounding these cosmic monsters. The magnetic fields threading through the hot gas appear to play crucial roles in launching the powerful jets of matter that stream away from many black holes at nearly the speed of light. Yet even as these spectacular confirmations of Einstein's theory accumulate, subtle hints suggest that our understanding of space-time may still be incomplete. Recent observations using gravitational lensing the bending of light by massive structures have revealed small but potentially significant deviations from Einstein's predictions on the largest scales in the universe. Teams studying data from the Dark Energy Survey have found that the strength of gravitational lensing appears to be about 1% weaker than Einstein's theory predicts, but only for observations looking back 5 to 6 billion years in cosmic time. This epoch coincides remarkably with when the expansion of the universe began to accelerate due to the mysterious force we call dark energy. The discrepancies are small, at the threshold of statistical significance, but they appear consistently across different analysis methods and datasets. Some theorists propose that this represents a fundamental modification to gravity on cosmic scales, a weakening of gravitational effects over distances of billions of light years. Others suggest it may indicate that our universe's space-time is more complex than Einstein envisioned, perhaps requiring mathematical frameworks beyond the relatively simple curved geometries of general relativity. Advanced mathematical approaches like Finsler geometry allow for space-times where distances might depend on direction, creating a kind of cosmic grain or texture in the fabric of reality. Some solutions to field equations in these more general theories predict gravitational wave signatures that are consistent with all of LIGO's detections, while potentially explaining the subtle deviations seen in cosmic observations. The Dark Energy Spectroscopic Instrument has been mapping nearly 6 million galaxies across 11 billion years of cosmic history, creating the most detailed three-dimensional map of large-scale structure ever assembled. This survey tests Einstein's theory by measuring how structures grow over time under the influence of gravity and dark energy. The results generally support general relativity, but hint at complexities that may require modifications or extensions to Einstein's framework. These potential deviations from Einstein's theory should not be seen as failures of general relativity, but as signposts pointing toward an even deeper understanding of reality. Einstein himself was acutely aware that his theory was incomplete, unable to reconcile the smooth space-time of general relativity with the quantum mechanical description of matter and energy. The search for quantum gravity, a theory that would unite Einstein's geometric vision with the probabilistic world of quantum mechanics, remains one of physics' greatest challenges. At the smallest scales, the Planck length of about 10 to the minus 35 meters and Planck time of about 10 to the minus 43 seconds, quantum fluctuations should make space-time itself turbulent and foamy, with virtual particles popping in and out of existence and creating a constantly changing geometry. Several approaches to quantum gravity suggest that space-time itself might be emergent, arising from more fundamental quantum processes. In some theories, the smooth fabric of space-time emerges from quantum entanglement, the mysterious connection between particles that Einstein called spooky action at a distance. The geometry of space might literally be woven from quantum correlations, with the strength of entanglement between different regions determining the distances between them. Other approaches treat space-time as arising from quantum error correction, similar to how classical computers protect information from corruption. In this view, the local physics we observe emerges from quantum codes that preserve information across the bulk of space-time, with gravity arising as a kind of error-correcting force that maintains the integrity of the quantum information. The holographic principle, emerging from studies of black holes, suggests an even more radical possibility. All the information contained in any volume of space-time might be encoded on its two-dimensional boundary, like a hologram that appears three-dimensional when viewed properly. This would mean that our familiar three-dimensional space is itself an illusion, a holographic projection of information stored on a distant surface. These ideas connect Einstein's geometric vision of gravity with quantum information theory in ways that might have seemed like pure fantasy just a few decades ago. They suggest that space, time, matter, energy, and information are all aspects of a deeper underlying reality that physicists are only beginning to glimpse. The discovery of gravitational waves has opened new windows for testing these fundamental ideas. Future space-based detectors like LISA, the Laser Interferometer Space Antenna, will be sensitive to gravitational waves with wavelengths of millions of kilometers, far beyond what Earth-based detectors can measure. These long wavelength gravitational waves could carry information from the very early universe, perhaps even from the epoch of cosmic inflation when space itself expanded faster than light. Such primordial gravitational waves would provide direct information about physics at energy scales comparable to those needed for quantum gravity, potentially revealing signatures of the discrete structure of space-time or the quantum processes that gave birth to our universe. They might tell us whether space-time is fundamentally smooth as Einstein envisioned or granular at the smallest scales. The event horizon. Telescope continues to push toward even more extreme tests of general relativity. Future observations may capture the dynamics of matter falling into black holes in real time, showing how space-time responds to the most violent processes in the universe. Plans are underway to extend the telescope into space, potentially revealing the photon rings that general relativity predicts should circle every black hole like onion layers of increasingly bent light. Perhaps most intriguingly, astronomers are beginning to search for signs of new physics in the vicinity of black holes. Some theories predict that black holes might have additional structure beyond the event horizon, or that they might leak information in ways not anticipated by classical general relativity. The extreme gravitational fields near event horizons provide natural laboratories for testing the boundaries between classical and quantum physics. The nature of dark energy itself remains one of the deepest mysteries in our understanding of space-time. This mysterious component appears to fill all of empty space, creating a kind of cosmic anti-gravity that causes the universe's expansion to accelerate. Whether dark energy represents a cosmological constant as Einstein originally proposed, or something more dynamic that evolves over cosmic time, will profoundly influence the ultimate fate of our universe. Recent observations suggest that dark energy's properties may indeed be changing over time, evolving in ways that could dramatically alter the future evolution of space-time itself. If dark energy continues to strengthen, it could eventually overcome all other forces in the universe, stretching space so rapidly that galaxies would lose contact with each other, stars would be torn apart, and ultimately even atoms would be disrupted in a scenario cosmologists call the Big Rip. Alternatively, dark energy might decay or reverse its effects, potentially causing the universe's expansion to slow, stop, and eventually reverse into a big crunch. Some cyclical models suggest that our universe might be just one phase in an eternal sequence of expansions and contractions, with each cycle potentially giving birth to new laws of physics and even new dimensions of space-time. Yet, there are reasons for optimism that space-time possesses deeper symmetries and conservation laws that will prevent such extreme fates. The mathematical elegance of Einstein's equations hints at connections to other fundamental symmetries in physics, relationships that might become clearer as our understanding deepens. String theory, for example, suggests that our familiar space-time might be embedded in a higher dimensional reality with up to 11 dimensions, most of which are curled up so small we cannot detect them directly. In these higher dimensional theories, gravity might leak between dimensions, potentially explaining why it appears so much weaker than other fundamental forces. The weakness of gravity compared to electromagnetism or the nuclear forces has long puzzled physicists, but it might simply reflect the fact that gravitational effects are diluted across additional dimensions of space that we cannot perceive. Some models suggest that our entire universe might be a three-dimensional boundary layer, or brane, floating in a higher dimensional bulk space. In this scenario, matter and energy would be confined to our three-dimensional brane, but gravity would propagate through the full higher dimensional space. Such theories could explain not only the weakness of gravity, but also the mysterious properties of dark matter and dark energy. The search for experimental evidence of extra dimensions continues through precision tests of gravity at small scales, searches for deviations from the inverse square law, and studies of high-energy particle collisions that might produce particles escaping into extra dimensions. While no definitive evidence has emerged yet, the mathematical beauty and consistency of these theories continue to inspire new experimental approaches and observational strategies. As we stand at the threshold of a new era in fundamental physics, with quantum computers beginning to simulate complex quantum systems, space-based gravitational wave detectors preparing for launch, and ever more powerful telescopes coming online, we find ourselves in a position remarkably similar to Einstein's over a century ago. We have a beautiful, successful theory that explains an enormous range of phenomena with extraordinary precision, yet we sense that it is pointing towards something even more profound and comprehensive. The fabric of space-time continues to reveal new patterns, new symmetries, new connections between the cosmic and quantum realms. Each gravitational wave detection brings news of cosmic violence from billions of years in the past. Each black hole image reveals the extreme physics of curved space-time, and each precision test of general relativity either confirms Einstein's insights or points toward the places where his theory reaches its limits and something new must take its place. In the gentle curvature of space-time around every massive object, in the ripples that carry information about the most violent events in cosmic history, in the event horizons that mark the boundaries of causality itself, we find a universe far stranger and more beautiful than our everyday experience might suggest. Space and time are not merely the passive stage on which physics unfolds, they are active participants in every process, from the fall of an apple to the birth of galaxies. The story of space-time is still being written, with each new discovery adding chapters to our understanding of reality's deepest foundations. As we peer ever deeper into space and time, uncovering the secrets of black holes and gravitational waves, dark matter and dark energy, quantum entanglement and cosmic inflation, we are slowly assembling a picture of a universe that is simultaneously more comprehensible and more mysterious than we ever imagined. This brings us to explore how the fundamental forces that govern all matter and energy emerge from the geometric properties of space-time itself, and how these forces collaborate to create the rich tapestry of cosmic structure, from the smallest particles to the largest galactic clusters, all dancing to the rhythm of curved space-time across the cosmic deep. Picture this: a story so vast and profound that it contains every other story ever told or yet to be told. This is cosmology, the universe's greatest narrative, stretching from the first flicker of existence to the furthest reaches of space and time. It begins not with the familiar opening of Once Upon a Time, but with something far more extraordinary, a moment when time itself began. We live within this story, every breath we take unfolding inside a cosmos that has been writing itself for 13.8 billion years. The very atoms that make up your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, all of these were forged in the nuclear furnaces of ancient stars. You're literally made of stardust, a walking, thinking collection of elements that have travelled unimaginable distances through space and time to become part of this moment, this consciousness reading these words. Consider what that means. The carbon atoms in your DNA were created inside massive stars that lived and died billions of years ago, long before our solar system existed. Those stars collapsed in spectacular explosions, scattering these precious elements across the galaxy, where they eventually coalesced into new star systems, planets, and ultimately into you. This isn't poetry, this is physics. This is the documented history written in the periodic table. When we trace the journey of a single carbon atom in your body, we follow a path that spans eons. Perhaps it began inside a red giant star 20 times the mass of our Sun, somewhere in the Orion arm of the galaxy 8 billion years ago. For millions of years, that atom participated in the intricate nuclear dance happening in the star's core, where lighter elements fused together under unimaginable pressure and temperature. When that ancient star finally exhausted its fuel, it swelled to enormous size before exploding as a supernova, launching that carbon atom on a journey through interstellar space. For hundreds of millions of years, the atom drifted through the cosmic void, part of an expanding cloud of stellar debris. Eventually, gravity began to pull the cloud together again, along with hydrogen and helium left over from the Big Bang, and heavier elements from other stellar explosions. Slowly, over millions more years, a new star system began to form, our solar system, with the Sun at its centre and planets condensing from the surrounding disk of material. That carbon atom found its way into the early Earth, perhaps locked inside a meteorite that crashed into our planet's surface 4 billion years ago. Through geological processes, weathering, and the complex chemistry of early life, it eventually became part of the biosphere. It might have spent time as part of an ancient microbe, then dissolved in the ocean, then incorporated into a marine organism, then buried in sediment, then lifted up as part of a mountain range, then weathered away again. Eventually, through the vast cycles of Earth's carbon cycle, That atom found its way into a plant through photosynthesis, then into an animal that ate the plant, then back to the soil when the animal died, then into another plant, and finally, through the food you ate yesterday, into your body. Right now, as you read these words, that ancient traveller from the heart of a long-dead star is part of you, perhaps in a protein in your brain that's helping you process these very thoughts. This remarkable journey illustrates something profound about our place in the cosmos. We are not separate from the universe looking in. We are the universe itself, organised into a particular pattern that has become conscious. Every atom in your body is a cosmic immigrant, and together they form something that can contemplate the very story of their own origins. But the story reaches even deeper than stellar nuclear synthesis. If we could somehow travel backward through time, rewinding the expansion of the universe like a cosmic film running in reverse, we would witness galaxy clusters drawing together, then individual galaxies merging, then stars condensing back into primordial gas clouds. Keep going, and we reach a time when atoms themselves cannot exist, when the universe was so hot and dense that electrons and protons existed as a roiling plasma soup. This takes us to about 380,000 years after the beginning, when the universe had cooled enough for electrons to bind with protons, forming the first hydrogen atoms. This moment, called recombination, set the cosmic microwave background radiation free from the dense fog of plasma that was containing it. Before this, the universe was opaque, light scattering endlessly through the thick plasma. After recombination, it became transparent, and that ancient light has been travelling toward us ever since. The physics of recombination is elegantly simple yet profound. As the universe expanded, it cooled, following the same principles that make a compressed gas hot and an expanded gas cold. When the temperature dropped to about 3,000 degrees Kelvin, roughly half the surface temperature of the Sun, protons and electrons finally had little enough kinetic energy that electromagnetic forces could bind them together into neutral hydrogen atoms. This transition didn't happen everywhere at once. Like fog lifting from a landscape on a summer morning, patches of space became transparent at slightly different times, depending on local density variations. The cosmic microwave background captures a snapshot of this process, showing us the universe as it appeared during this cosmic dawn, when the first atoms formed and light could finally travel freely through space. We can see this light today, filling every cubic centimetre of space around us with faint microwaves. It's everywhere you look, though invisible to your eyes, a 2.7 Kelvin whisper from the universe's infancy. According to NASA, CMB fills the universe, and in the days before cable TV, every household with television could see the afterglow of the Big Bang. That static on old television sets. A small fraction of it was actually the cosmic microwave background, the oldest light in the universe flickering across your screen. Think about that for a moment. Every point in space around you right now contains photons that have been travelling since the universe was barely 380,000 years old. They carry within them a detailed map of how matter was distributed in the early cosmos. Tiny temperature fluctuations that reveal where the first structures began to form. These maps tell us with remarkable precision what the universe is made of. The cosmic microwave background is remarkably uniform, varying in temperature by only about 100,000th of a degree from place to place. This uniformity was initially puzzling because regions of sky on opposite sides of the universe appear to have the same temperature, even though they're so far apart that light from one could never have reached the other in the time since the Big Bang. How could they have the same temperature if they were never in contact? This is known as the horizon problem, and it's one of the great puzzles that led to the development of inflation theory. The solution requires something that seems to violate common sense. Periods in the early universe when space itself expanded faster than the speed of light. This doesn't violate relativity because space itself was expanding, carrying matter along with it, rather than matter moving through space. During inflation, regions that were once close enough to reach thermal equilibrium were suddenly stretched far apart, appearing today as widely separated patches of sky with the same temperature. It's as if you took a small uniform piece of fabric and stretched it to enormous size. The fabric would still appear uniform, but regions that were once next to each other would now be very far apart. Based on the 2013 data from the Planck mission, the universe contains 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. This means that everything we can see and touch, every star, planet, galaxy and nebula, every atom in your body, represents less than 5% of what exists. The rest is dark matter, an invisible scaffolding that shapes the cosmos, and dark energy, a mysterious force that's accelerating the expansion of space itself. Let's contemplate what these numbers really mean. If you could somehow gather all the matter in a sphere 1 billion light-years across, containing millions of galaxy clusters with their hundreds of billions of galaxies, each containing hundreds of billions of stars, plus all the gas, dust, planets, asteroids, comets, and every other bit of ordinary matter, it would represent less than 5% of the total mass energy in that volume. The remaining 95% is completely invisible to our telescopes, detectable only through its gravitational effects. Dark matter provides the scaffolding upon which all visible structure hangs, while dark energy provides the force that's driving the accelerating expansion of the universe itself. We're like inhabitants of a vast mansion who can see only one room out of 20, while the rest remains hidden behind walls we cannot penetrate. Dark matter doesn't interact with light or ordinary matter except through gravity, but its presence is written everywhere in the sky. Dark matter makes up most of the mass of galaxies and galaxy clusters, and is responsible for the way galaxies are organized on grand scales. It forms vast filaments spanning hundreds of millions of light-years, a cosmic web upon which galaxies gather like dewdrops on a spider's web. The cosmic web is one of the most striking features revealed by large-scale surveys of galaxy positions. When astronomers map the locations of millions of galaxies across billions of light-years, a remarkable pattern emerges. Galaxies are not randomly distributed through space, but instead form a vast network of filaments separated by enormous voids. These filaments can stretch for hundreds of millions of light-years, connecting massive clusters of galaxies like bridges spanning cosmic canyons. The structure resembles the neural network of a brain, or the mycelial network of a fungus, with dense nodes connected by thin filaments. The largest known structure, the Great Wall, stretches for more than 500 million light-years, containing thousands of galaxies arranged in a sheet-like pattern. These structures are so large that light takes hundreds of millions of years to cross them, meaning they formed when the universe was much younger. Computer simulations of dark matter evolution show how this cosmic web formed. In the early universe, dark matter was distributed almost uniformly, with only tiny density variations. Over billions of years, gravity amplified these small differences. Slightly denser regions attracted more matter, becoming denser still, while matter flowed out of less dense regions, leaving them nearly empty. The result is the filamentary structure we see today, with galaxies forming where dark matter filaments intersect and merge. But even more mysterious is dark energy. Dark energy, meanwhile, is the name we give the mysterious influence driving the accelerated expansion of the universe. In 1998, astronomers studying distant supernovae made a shocking discovery. They expected the universe's expansion to be slowing down due to gravity, but instead they found it was speeding up. Something was pushing space apart, and that something comprises more than 2/3 of everything that exists. The discovery came from observations of Type Ia supernovae, stellar explosions that serve as cosmic distance markers because they all reach roughly the same peak brightness. By measuring how bright these supernovae appear compared to how bright they should be at their known distances, astronomers can determine how fast the universe was expanding at different times in the past. The results were completely unexpected. Supernovae from billions of years ago appeared dimmer than predicted, meaning they were farther away than expected if the universe's expansion had been slowing down. Instead, the expansion had been accelerating, as if some unknown force was working against gravity on cosmic scales. This force was dubbed dark energy, though nobody knows what it actually is. Several possibilities have been proposed. Dark energy might be a property of space itself, what Einstein called the cosmological constant, a sort of built-in tendency for space to expand. Or it might be a dynamic field, similar to the field thought to drive inflation, but operating much more weakly. Some theories suggest that our understanding of gravity itself might need modification on the largest scales. This discovery earned the Nobel Prize, but it also revealed how little we truly understand about our cosmos. We've given these invisible components names, dark matter and dark energy, but the word dark here doesn't mean they absorb light. It means they're unknown, mysterious, perhaps the greatest puzzles in all of science. Imagine standing in a library where you can only read less than 5% of the books, while 95% are written in languages you cannot decipher. That's our situation with the universe, yet from that small fraction we can read, we've reconstructed an extraordinary story. The tale begins with inflation, a period lasting less than the tiniest fraction of a second, when the universe expanded faster than light itself. Alan Guth introduced the inflationary model in 1979 to explain why the universe is flat and homogeneous, proposing that the universe underwent a period of rapidly accelerating expansion a few instants after the Big Bang. During inflation, quantum fluctuations, tiny ripples in the fabric of spacetime, were stretched to astronomical proportions, becoming the seeds from which all future structure would grow. The idea of inflation emerged from attempts to solve several puzzles about the universe's properties. Besides the horizon problem, there was the flatness problem, why the universe appears to be geometrically flat rather than curved. In Einstein's general relativity, the geometry of space depends on the density of matter and energy it contains. If the density is exactly equal to a critical value, space is flat. If it's higher, space curves inward like the surface of a sphere. If it's lower, space curves outward like a saddle. Observations show that our universe is flat to within a fraction of a percent, which seems like a remarkable coincidence. In the early universe, the density would have had to be fine-tuned to within 1 part in 10 to the 60th power to produce the flat universe we observe today. This is like balancing a pencil on its point for billions of years, an extraordinarily unlikely occurrence unless something made it happen. Inflation solves this problem elegantly. During the inflationary period, space expanded so rapidly that any initial curvature was stretched flat, just as the surface of a balloon appears flat to an ant, even though the balloon itself is curved. No matter what the initial geometry was, inflation would have made it appear flat to us today. The inflationary period also solved the magnetic monopole problem. Many theories in particle physics predict the existence of magnetic monopoles, particles that would be like isolated north or south magnetic poles, rather than the dipoles we observe. These should have been produced abundantly in the early universe, but none have ever been found. Inflation explains their absence by diluting their density to essentially zero through the rapid expansion of space. During inflation, quantum fluctuations, tiny ripples in the fabric of spacetime, were stretched to astronomical proportions, becoming the seeds from which all future structure would grow. These quantum ripples started smaller than a proton, but were expanded to sizes larger than galaxies, providing the density variations that would eventually become the cosmic web of matter we see today. These quantum ripples, amplified by inflation, eventually became the slight density variations we see in the cosmic microwave background. Regions that were slightly denser began to attract more matter through gravity, slowly growing into the first stars, then galaxies, then the vast cosmic web we observe today. The inflationary theory makes specific predictions about the properties of these fluctuations that can be tested by observations of the cosmic microwave background. The fluctuations should be nearly scale invariant, meaning they have roughly the same amplitude on all scales, and they should follow a nearly perfect Gaussian distribution. Both predictions have been confirmed by observations from WMAP and Planck satellites. But here's where the story takes a truly mind-bending turn. Almost all versions of inflation are eternal. Once inflation starts, it never stops completely. Inflation has ended in our part of the universe, but very far away one expects that inflation is continuing and will continue forever. This leads to the concept of eternal inflation, where new universes are constantly bubbling into existence, each with potentially different physical laws and properties. The mathematics of eternal inflation are both elegant and disturbing. In most inflationary models, while inflation ends in some regions of space, it continues in others. The regions where inflation continues expand exponentially, always producing more volume where inflation is still occurring. New pocket universes constantly bud off from this eternally inflating background, each beginning its own Big Bang like the one that created our observable universe. According to this theory, we are living in one of these pocket universes, And even though the pocket universes keep forming, there's always a volume of exotic repulsive gravity material that can inflate forever, producing an infinite number of these pocket universes in a never-ending procession. If this is true, our entire observable universe, containing hundreds of billions of galaxies, each with hundreds of billions of stars, might be just one bubble in an infinite cosmic foam. The implications are staggering. In an infinite multiverse, every possible variation would exist somewhere. There would be universes where the constants of physics are slightly different, where stars cannot form, or where different types of matter dominate. There might be universes where you made different choices, or where Earth never formed, or where entirely different forms of life evolved under alien skies. Some of these variations would be subtle. Perhaps there's a universe where the electromagnetic force is slightly stronger, making atoms smaller and chemistry more energetic. Others might be dramatic, with universes where the strong nuclear force is too weak to bind protons and neutrons together, preventing the formation of atomic nuclei entirely. The multiverse concept raises profound questions about the nature of existence and scientific explanation. If anything that can happen does happen somewhere in the multiverse, then our universe's apparent fine-tuning for life might be explained by what's called the anthropic principle. We observe a life-friendly universe simply because we exist to observe it. Universes without observers would exist too, but there would be no one there to notice them. Yet the multiverse idea remains controversial among physicists. Some argue that if we cannot observe these other universes, even in principle, then they fall outside the realm of science. Others contend that the multiverse is a natural consequence of our best theories and should be taken seriously even if it cannot be directly tested. But let's return to our own cosmic neighbourhood, where recent observations have revealed surprises that challenge our understanding of how the universe evolved. The James Webb Space Telescope has detected a galaxy that existed just 280 million years after the Big Bang, designated MOM-Z14, currently the earliest and most distant galaxy ever detected. This discovery is extraordinary because when astronomers got their first glimpses of galaxies in the early universe from NASA's James Webb Space Telescope, they were expecting to find galactic pipsqueaks, but instead they found what appeared to be a bevy of Olympic bodybuilders. Some galaxies appeared to have grown so massive, so quickly, that simulations couldn't account for them. The James Webb Space Telescope has revolutionized our understanding of the early universe in ways that continue to surprise astronomers. Its infrared vision allows it to see light that has been redshifted by cosmic expansion, revealing galaxies so distant that their light has been traveling toward us for more than 13 billion years. What the telescope has found challenges many assumptions about how galaxies form and evolve. The early universe appears to have been much more dynamic and active than theoretical models predicted. Galaxies seem to have assembled more quickly, grown more massive earlier, and begun forming stars at a prodigious rate much sooner than expected. These early galaxies are rewriting the textbook on cosmic evolution. The galaxy designated JD's GS Z140 is unexpectedly bright and chemically complex for an object from this primordial era, containing significant amounts of oxygen, which suggests the galaxy had been forming stars for potentially 100 million years before it was observed. To create oxygen, multiple generations of stars must have formed, lived their lives, and exploded as supernovae, enriching space with heavy elements, all within the first few 100 million years of cosmic history. The presence of heavy elements in these early galaxies tells a remarkable story of rapid stellar evolution. The first stars in the universe were probably very different from the Sun, massive giants containing only hydrogen and helium from the Big Bang. These population 3 stars, as astronomers call them, would have been hundreds of times more massive than the Sun, burning their nuclear fuel in just a few million years before exploding as supernovae. When these first stars died, they seeded space with heavier elements, enabling the formation of a second generation of stars more similar to those we see today. The fact that we observe oxygen and other heavy elements in galaxies seen just a few 100 million years after the Big Bang means this entire cycle of stellar birth, evolution and death must have happened very quickly in the early universe. This pushes back the timeline for when the first galaxies could have formed and suggests that the universe was far more active in its infancy than we previously imagined. Using deep field images from NASA's James Webb Space Telescope, researchers at the University of Missouri identified 300 unusually bright objects in the early universe that shine far brighter than current models of early galaxy formation predict. These mysterious objects raise fundamental questions about galaxy formation in the first few 100 million years after the Big Bang. If they truly are galaxies, they suggest that massive stellar systems could assemble much more rapidly than current theory allows. Alternatively, they might represent entirely new types of cosmic phenomena that we haven't yet learned to recognize. The discoveries don't stop there. An international team of astronomers has identified bright hydrogen emission from a galaxy in an unexpectedly early time in the universe's history, challenging researchers to explain how this light could have pierced the thick fog of neutral hydrogen that filled space at that time. This suggests that the era of reionization, when the first stars cleared the cosmic fog, began much earlier than theorists predicted. The era of reionization represents one of the most dramatic transitions in cosmic history. For hundreds of thousands of years after recombination, the universe was filled with neutral hydrogen gas that absorbed ultraviolet light. The cosmos was dark, lit only by the fading glow of the cosmic microwave background. This period is sometimes called the Cosmic Dark Ages, when no stars shone and no galaxies existed. Eventually, the first stars began to form within dark matter halos, igniting nuclear fusion and beginning to shine. These early stars emitted intense ultraviolet radiation that began to ionize the surrounding hydrogen gas, creating bubbles of transparency around each star. As more stars formed and these bubbles expanded and merged, the entire universe gradually transitioned from opaque to transparent. This process should have taken hundreds of millions of years to complete, but observations suggest it began much earlier than expected. The discovery of bright hydrogen emission from the galaxy JADAS GS 13-1, observed just 330 million years after the Big Bang, shows that at least some regions of space had already become transparent much sooner than theoretical models predicted. These revelations remind us that the universe is full of surprises, that even our most sophisticated theories and models can be challenged by new observations. Each discovery opens new questions, new mysteries to explore. We thought we understood how galaxies form and evolve, but the early universe seems to have been far more dynamic and complex than our simulations suggested. The rapid pace of early cosmic evolution may also help explain some puzzling observations about supermassive black holes. The James Webb Space Telescope has found black holes in early galaxies that are much more massive than expected for their age. In the modern universe, there's typically a relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. But these early black holes seem disproportionately large. How did these black holes grow so massive so quickly? One possibility is that they formed from the collapse of the very first stars, then grew rapidly by accreting matter from their surroundings. Another is that they formed through the direct collapse of gas clouds in the early universe, skipping the stellar formation stage entirely. Understanding how these supermassive black holes formed so early will require new theoretical models and more observations. Yet perhaps the most profound aspect of this story is not just what we've discovered, but how we've discovered it. We've learned to read the universe like a vast book, extracting its secrets from light that has travelled billions of years to reach us. Every photon carries information about where it came from and what it encountered on its journey through space and time. When we look at distant galaxies, we're not just seeing objects in space, we're looking backward through time itself. Light from a galaxy 10 billion light-years away shows us what that galaxy looked like 10 billion years ago, when our own Milky Way was still forming. The universe has become a time machine, allowing us to study cosmic archaeology by observing increasingly distant objects. This temporal archaeology has revealed the universe's evolution from a smooth, nearly featureless beginning to today's rich tapestry of structures. The cosmic microwave background shows us the universe when it was only 380,000 years old, nearly smooth except for tiny fluctuations that would eventually grow into galaxies. The first galaxies appeared within a few 100 million years, initially small and irregular but growing larger and more structured over cosmic time. By studying galaxies at different distances and therefore different ages, astronomers can trace the evolution of cosmic structure like paleontologists, studying fossils from different geological eras. They see how galaxies assembled from smaller building blocks, how the first black holes formed and grew, how heavy elements were created and distributed throughout space. This cosmic evolution is an ongoing process. Even today, galaxies continue to grow through mergers and accretion of surrounding matter. Our own Milky Way is currently in the process of merging with several smaller satellite galaxies and is on a collision course with the Andromeda Galaxy, though that encounter won't occur for another 4.5 billion years. After the Big Bang, gas in the universe was incredibly hot and dense. Over hundreds of millions of years, the gas cooled. Then, the universe hit repeat. The gas again became hot and ionized, likely due to the formation of early stars and galaxies, and over millions of years became transparent. The story is one of increasing complexity, of simple beginnings giving rise to structures of stunning intricacy. From the first hydrogen atoms to the first stars, from the first galaxies to the cosmic web of dark matter filaments spanning billions of light years, the universe has been building complexity for nearly 14 billion years, and the most complex structures we know of are biological, the intricate chemistry of life itself, which as far as we know has arisen at least once in this vast cosmos here on Earth. This increasing complexity represents one of the universe's most remarkable features. The laws of physics and chemistry that govern cosmic evolution seem naturally inclined to produce structure and organization. Gravity pulls matter together into clumps. Nuclear fusion in stellar cores creates heavier elements from lighter ones. Supernovae distribute these elements throughout space, enriching the raw material from which new stars and planets can form. On Earth, this process continued with the emergence of chemistry more complex than anything seen elsewhere in the cosmos. Carbon, oxygen, nitrogen, and other heavy elements, forged in stellar cores, combined in intricate ways, eventually giving rise to the self-replicating molecules that would become the foundation of life. Through billions of years of evolution, these simple beginnings led to the emergence of consciousness itself, minds capable of contemplating their own cosmic origins. But the universe's story is far from over. Current observations suggest we live in a universe dominated by dark energy, which means the expansion will continue to accelerate forever. Billions of years from now, galaxies will be so far apart that beings living in any one of them will see a dark, nearly empty universe with only their local galaxy group visible against the cosmic night. The cosmic microwave background will have cooled and redshifted beyond detection, and future cosmologists may have no way to deduce the universe's fiery beginning. This future cosmic isolation represents one of the strangest implications of dark energy's dominance. As the expansion accelerates, distant galaxies will recede beyond the cosmic horizon, their light redshifted to such long wavelengths that it becomes undetectable. Eventually, observers in any given galaxy will see only their local group of gravitationally bound galaxies against a perfectly dark sky. The cosmic microwave background, currently observable as a faint glow filling all of space, will become so redshifted that it falls below the threshold of detectability. Future astronomers will have no evidence of the Big Bang, no way to deduce that their local galaxy group is part of a much larger universe that was once hot, dense, and uniform. Stars will continue to form for trillions of years, but eventually the universe will run out of hydrogen fuel. Red dwarf stars, the smallest and longest lived, will be among the last to shine, potentially burning for tens of trillions of years. After they fade, the universe will enter what cosmologists call the degenerate era, where only stellar remnants, black holes, and elementary particles remain. Even then, the story doesn't end. Quantum mechanics suggests that even protons may eventually decay, given enough time, perhaps in 10 to the 34th power years or more. Black holes will slowly evaporate through Hawking radiation, with the largest taking 10 to the 100th power years to completely disappear. In the end, the universe may contain only elementary particles in a state of maximum entropy, but even that ending is uncertain. Recent theoretical work suggests alternative possibilities. Some researchers propose that our universe emerged from the interior of a black hole formed within a larger parent universe, calling this the black hole universe model, which offers a radically different view of cosmic origins grounded entirely in known physics and observations. Rather than beginning from nothing, this model suggests our universe is part of an eternal cosmic cycle shaped by gravity and quantum mechanics. The idea is that the universe is actually eternal, existing at all times, so there is no beginning to explain. The laws of physics themselves don't seem to make any significant distinction between the future and the past. In this view, what we call the Big Bang was not the birth of everything, but rather a transition in an eternal cosmos, perhaps the result of a gravitational collapse followed by a quantum bounce. These new ideas challenge our most basic assumptions about existence itself. Did the universe have a beginning, or has it always existed in some form? Are we part of a single cosmos or an infinite multiverse? These questions push the boundaries of science into the realm of philosophy, reminding us that even as we learn more about the universe, deeper mysteries remain. Consider the sheer improbability of your existence within this cosmic story. For you to be here, reading these words, the universe had to evolve in precisely the way it did. The fundamental constants of physics had to have exactly the right values to allow stars to form and create heavy elements. Earth had to form at exactly the right distance from the Sun, with exactly the right conditions for liquid water and eventually life. The fine-tuning of physical constants appears remarkably precise. If the strong nuclear force was slightly weaker, atomic nuclei couldn't hold together, and stars couldn't create heavy elements. If it was slightly stronger, hydrogen would rapidly fuse into heavier elements in the Big Bang, leaving no fuel for stars. If the electromagnetic force were different by more than a few percent, chemistry as we know it would be impossible. The expansion rate of the universe also appears finely tuned. If the universe had expanded slightly faster in its early moments, matter would have been too dilute for gravity to pull it together into galaxies and stars. If it had expanded slightly slower, the universe would have collapsed back on itself before stars could form. The balance is so delicate that changing the expansion rate by 1 part in 10 to the 60th power in the early universe would have prevented structure formation entirely. The chain of events stretching from the first moments after the Big Bang to this present moment is so intricate, so dependent on countless precise conditions, that it seems almost miraculous. Yet here you are, a conscious being capable of contemplating the very cosmos that gave birth to you, made of atoms forged in the hearts of ancient stars, living on a planet orbiting one of hundreds of billions of stars in a galaxy that's one of hundreds of billions of galaxies in the observable universe. This is perhaps the most remarkable aspect of the universe's story, that it has become conscious of itself through beings like us. We are the universe's way of knowing itself, of understanding its own history and evolution. Through science, we've learned to decode the messages written in starlight, to read the history preserved in cosmic background radiation, to understand how the simplest beginnings gave rise to the magnificent complexity we see around us. The development of consciousness represents what may be the universe's most extraordinary achievement, from the quantum fluctuations of inflation to the formation of galaxies, from stellar nucleosynthesis to planetary formation, from the emergence of chemistry to the origin of life, from biological evolution to the development of intelligence. The cosmos has produced minds capable of understanding their own cosmic context. The story of cosmology is ultimately the story of us, of how we came to be and how we fit into the grand scheme of existence. It's a story that begins with pure energy and ends, for now, with consciousness contemplating its own cosmic origins. Every star that shines, every planet that forms, every galaxy that spirals through space is part of this vast narrative of which we are both products and witnesses. As we continue to probe deeper into space and further back in time, who knows what new chapters of this cosmic story we'll uncover? Perhaps we'll discover signs of life elsewhere in the universe, confirming that consciousness is not unique to Earth, but a natural outcome of cosmic evolution. Perhaps we'll detect gravitational waves from the Big Bang itself, or find evidence of other universes beyond our own. The search for these answers drives some of the most ambitious scientific projects in history. Future space telescopes will peer even deeper into the cosmic past, perhaps glimpsing the very first stars to shine in the universe. Gravitational wave detectors may eventually become sensitive enough to detect the primordial waves generated during inflation itself, providing direct evidence for this crucial phase of cosmic evolution. Ground-based telescopes are growing ever larger and more sophisticated, with projects like the Extremely Large Telescope promising to reveal Earth-like planets around nearby stars and study their atmospheres for signs of life. Meanwhile, theoretical physicists continue developing new models that might explain dark matter and dark energy, or reveal the quantum nature of gravity itself. What remains certain is that the universe's greatest story is still being written, still unfolding through billions of years of cosmic time, and remarkably, improbably, wonderfully, we are here to witness it, to participate in it, to help tell it. Each new discovery adds another page to this cosmic narrative, revealing new depths of beauty and complexity in the universe that gave birth to us.